All right, there we go. So today's schedule is I'm going to complete the video I was showing last time on hypothesis testing, pre-recorded video. And so I'll complete that, and then we'll go right into StatKey, start learning how to use StatKey to do hypothesis tests. And we'll continue with that on Thursday. And that will complete all the knowledge that we learned in this course. That's it. And after that's completed, next Tuesday, we will have the last quiz, quiz number 9 on hypothesis test. Again, a StatKey type quiz, just like the one that you took on confidence intervals. And then we'll have a review for test number 3 next Tuesday. And then test number 3 will be a week from Thursday. The Thursday is let's see, this coming Thursday, 22nd, so the 29th will be the test number 3. Now, since we're getting to the end of the semester, it's absolutely essential that you attend test number 3 because there's no time for makeups or anything like that. The semester's pretty much ending.
What's the date of the test number 3 is the final, correct?
No, test number 3 is not the final exam. It's test number 3.
What's test number 3 is when?
A week from Thursday, 29th.
29th.
Yeah.
Okay, all right. I'll stay after to talk to you.
Yeah. So the 29th is test number 3. Following Tuesday will be our final exam. Once again, you have to be there. All right, the semester's ending. And I'm going to be submitting grades very quickly. So my goal is to have your grades submitted by no later than early Wednesday morning. Because I'm going to be, my wife and I have some personal business. We're going to be leaving the area on Thursday. So, and also there's graduation that weekend. So there's a tremendous incentive for me to get the grades in quickly. If for some reason there's a conflict as far as test 3 or the final exam is concerned, you must take those earlier than everybody else, not later. Now, if there's some issue with emergencies with COVID or anything like that, then what you'll have to do is obviously notify me. And then you'll need, if it's COVID and you can't take the final or can't take the test number 3 because of it, then I will probably have to give you an incomplete for the course, as long as you're passing. If you're not passing, then it won't make any difference. But if you are passing, I will give you an incomplete, and then you can finish the course later when everything is better for you. All right. I'm going to be out of the area for a couple of weeks. We'll be back in the area around May 20th or so. So if there is an incomplete, then that would be the time. I mean, you're given obviously additional time, but that would be a time to consider completing the course at that point, if you're available to complete it. All right, but that's it. So you know, as far as finals are concerned, you have to attend, even if you're not feeling well. All right, that's the whole point of final exams, is that's it. The semester's over. So, and you all know that, unless this is the first semester at Rowan, you all know that's the case. All right, any questions about our schedule? And once again, any conflicts with test 3 or the final exam, you need to let me know as soon as possible, and you'll need to take those tests earlier than everybody else, not later. Okay? All right. I guess there's nothing else anybody wants to talk about. All right, so what I'm going to do now is, give me a second here. I'll try to get back to that video that we were looking at before. So let's see if I can find it again. Give it a minute. go. All right. So now you won't hear anything or anything at the moment. I'm going to cue it up to where we stopped last time. All right. So here we go. I'm going to share the screen and also the sound. All right, so people, you need to turn your videos on so I can see you. You can't give me a thumbs up if I can't see you. So, Aaliyah and Bianca, there we go, Diana. You see it? Give me a thumbs up. Yep, good. All right, so you should be able to hear it. Let me turn it on. Hopefully you'll be able to hear the sound also.
It's unknown. So I hope you understand these two different things here in this chart.
I'm going to actually go back a little bit.
Along the left here is the result of the statistical test. We're either going to reject the null hypothesis from the data or we're not going to reject the null hypothesis. Up here, along these columns here, is the actual unknown reality. In reality, either the null hypothesis is true or it's not true. Simple as that. Now, Dr. Williams mentioned two types of errors that are possible in a hypothesis test. The first one is called a type 1 error. It's in this box here. See, there's 4 boxes. This box here is an intersection of this row, where we're rejecting the null hypothesis, and this column, where we are stating that in reality, the null hypothesis is true. So this is an error, right? If our test says there's enough evidence to reject the null hypothesis, and yet in reality, the null hypothesis is true, that's an error. And that's what she called a type 1 error. Now, if you reject the null hypothesis and the null hypothesis is false, well, you made a correct decision, didn't you? Now, you don't know that, obviously, since the reality is unknown. But if you happen to reject the null hypothesis and the null hypothesis is false, that means that the test that you did is correct. It was a correct decision. Now, suppose that there was not enough evidence to reject the null. Okay. And suppose the null hypothesis is true. So that's this box here, the intersection of the intersection of this column, that the null hypothesis is true, and that we don't reject it. So if we don't reject the null hypothesis, and it's actually true, that's also a correct decision. Okay. However, if we do not reject the null hypothesis, and the null hypothesis is actually false, then that is also an error. That's this box here, the intersection of this row and this column. And that's what you call a type 2 error. So let me review the type 1 error again. The type 1 error is when we reject the null hypothesis, when the null hypothesis in reality is true. And a type 2 error is the case where we don't reject the null hypothesis, but the null hypothesis is actually false. We should have rejected it, but we didn't. All right. So those are the two types of errors. The other two decisions are correct decisions. Now, she used the courtroom analogy. So if the null hypothesis is that the person, if the null hypothesis is true, that means the person did not commit the crime. All right. But suppose they get convicted. In other words, the jury rejects the idea that they're innocent and says there's enough evidence to show that the person committed the crime beyond a reasonable doubt, then we've created this error. We reject the null hypothesis, which means we're going to send the person to jail, when in reality the person's innocent. So that's a type 1 error. Using the same courtroom analogy, if H naught is false, now remember H naught, the null hypothesis is the person is innocent. So suppose H naught is false, which means the person committed the crime, but there's not enough evidence to convict, right? Which is this here, we do not reject the null. Then we've committed this type 2 error. And in this case, what happens? The person doesn't go to jail when they should have gone to jail because they committed the crime. In other words, a guilty person has been let free to maybe commit another crime in society. In my view, probably as far as society is concerned, a type 2 error is worse, right? Because you're letting a criminal back into society. As far as the criminal, the person himself is or herself is concerned, type 1 error is the worst thing, because if the person's actually true and got convicted, that means you're going to jail for a crime that they didn't commit. All right. Now, Dr. Williams also mentioned this idea of alpha, the probability of a type 1 error. So the probability that you committed a type 1 error, that is, you reject the null hypothesis when the null hypothesis is actually true, it's called alpha. We use the Greek letter alpha to represent this probability of a type 1 error. The other type of error she mentioned, probability of a type 2 error, where we do not reject the null hypothesis when the null hypothesis is actually false, that's called beta. All right, so the beta is the probability of the type 2 error, alpha is the probability of a type 1 error. By the way, just for your own information, there's also a term called the power of the test. Now, a researcher, they're always trying to reject the null hypothesis because they have a different view than the standard view of the world, right? That's why they're doing the research. They believe there's an alternative explanation for something. So their job, their goal, hopefully, without any sort of manipulation, is to reject the null hypothesis when the null hypothesis is actually false, right? That's a correct decision. This one up here. They want to reject the null hypothesis, that's their goal, and they're hoping the null hypothesis is actually false. And that probability is called the power of the test, all right? The power of the test is the probability that we reject the null when it's actually false, that particular correct decision. Now, this is an advanced topic, which for those of you in the statistical literacy course, I won't go into any further. Just know that that's the definition of it. For those of you in the Camden County course, I will go into it a little further with you guys, all right? Because it's more of an advanced topic. All right, now the alpha, that's the probability of a type 1 error, is also called the level of significance. The level of significance. Now, why do we call it that? Because that's the amount of type 1 error that we can, as a researcher, tolerate. I think Dr. Williams mentioned that, right? If you pick 0.05, you pick some small number, like 0.05, which is a 5% level of significance. We're basically saying that when we reject the null hypothesis, we can live with up to a 5% alpha error, type 1 error, because 5% is okay. We can't get it to 0%, but 5% is okay. And we know that in 95% of the time, we'll get it right, all right, when we reject the null hypothesis. In other words, the power of the test will be good. Now, so what happens in reality is a researcher is going to determine this alpha up front before they do the research. Now, typically in different fields of study, there's a standard alpha that's picked by researchers in that field. Many fields pick 0.05 or a 5% level of significance, but there could be some fields in the sciences especially where you pick a 1% level of significance. But you do this before you begin your research. That's typically when you do it. So what Dr. Williams was about to show you using formulas was this following idea. The idea is that by using alpha in a particular way, and again, I will show this to you guys next week, and either through StatKey or through formulas, you're going to use alpha. And what you're going to do is that by using this alpha, this level of significance, we can determine if the sample value that we get from the sample, right, the sample value from the variable of measurement, or if it's the proportions, the sample proportion, what we're going to determine is this value that we come up with from the sample sufficiently far away from the hypothesized value of the null hypothesis to make it unlikely that the null hypothesis value is true. In other words, for example, like the example we had before, let's just go back in the previous page. Suppose the null hypothesis is that the population mean is equal to 5. Suppose we get from our sample data, a sample mean of 7. Now we know 7 is bigger than 5, but the question is it significantly bigger than 5, so that it's highly unlikely that if the true mean is 5, we would have gotten a sample mean of 7. Okay, that's really what we're asking. If the true mean is really 5, okay, but we got a value of 7 in our sample as the mean, is 7 so much bigger than 5 that we think it's highly unlikely that we would have gotten a 7 in our sample when the true population mean is 5. Remember, a sample is just a subset of a population. So if the sample mean is, population mean is 5, which we don't know, but we're guessing that's what it is, okay? But we get a sample mean of 7, we have to start thinking, is 7 so much bigger than 5 that we think it's highly unlikely that the true population mean is 5. If we come to that conclusion through the methods that I will show you, then we will reject the null hypothesis and say, we think there's enough evidence through the sample mean of 7 to conclude that the population mean must be greater than 5. All right, I hope you get the idea there. So is the sample statistic that we calculate, the mean or the proportion, sufficiently far away from the population mean that we decide that this can't be sampling variability from the population mean? It must mean that the true population mean is something different than 5, in this case, greater than 5. All right. So this will become clear when we actually do some examples. All right. So that's the key. Is it sufficiently far away? If this is the sample statistic sufficiently far away from the population parameter that we can justify rejecting the null hypothesis and saying the alternative hypothesis is true. Now, there are 3, as Dr. Williams showed, there's 3 types of hypothesis tests. There is there's the 3 types are called the two-tail test. Now she called what I call the left tail test the lower tail test, but just it means the same thing. I'm just referring to the left tail, as she's calling it the lower tail. It means the same thing. And the other type of test is the right tail test, which she called the upper tail test, which is the tail on the right. So what does this mean? What does it mean? Well, whatever problem we're going to be working on in hypothesis tests, whatever problem we're going to be working on, we're going to have a pair of hypotheses from the way the problem is written up. The problem in the wording of the problem will determine the null and alternative hypothesis. Again, you'll see examples of this next week, okay? Beginning next week. So, for example, let's say mu is equal, the population mean is equal to 10 is our null hypothesis, and that the alternative hypothesis is mu is not equal to 10. That is, it's either lower than 10 or bigger than 10. Suppose we pick alpha equal to 0.05. Alpha is 0.05. That's our level of significance. We determine that up front, right? We want to pick that as the probability of our type 1 error. We're tolerating 5% of the times when we reject the null hypothesis. We're okay with it, the fact that 5% of the time when we reject the null hypothesis, that we're making a mistake, that the null hypothesis is actually true. So how do we actually do this? Well, we have our bell-shaped curve, okay? Bell-shaped curve, and for those of you in the course, the statistical literacy course, when we create our randomization test, we'll create something that looks like a bell-shaped curve, just like we did with hypothesis tests. So for a two-tailed test, if the alternative hypothesis is saying that mu is not equal to 10, and we're using alpha as 0.05, what we're doing basically with the two-tailed test is we're going to take our alpha of 0.05, which is 5%, and we're going to split it into two. We're going to divide it into two equal pieces. Half of the 5% is going to go to the left tail, and half of the 5% is going to go to the right tail. I'm just coloring in those two tails there. And half of 5% is 2.5% in each tail. Now, we're going to call this region in here and this region over here the rejection regions. And the region in the middle between these two values here, between these two vertical lines here, we're going to call that the non-rejection region. So what does that mean? Well, the mean, the hypothesized mean is 10. So that's going to be in the middle. That's going to be our hypothesized mean in the middle. What we're saying basically is, if the sample statistic, suppose the sample statistic is 15. I'm just making that up, right? Positive 15. And suppose 15 is somewhere along this line. It's bigger than 10, but it's to the right of this vertical line here. It's somewhere over here. The value of x, this is x here, what we're measuring, is in this region here, right? Here's the deal. If the value of x is in this region here, where we're shading the tail here, in this so-called rejection region, that means we're going to reject the null hypothesis, and we're going to accept the alternative hypothesis. In other words, the value of 15 is sufficiently away from 10, where it's in this so-called rejection region. Alternatively, let's say somebody else does a sample, and you find that your sample mean is 5 instead of 15. Suppose 5 is inside this region here, all right, inside this region. This is also a rejection region for a two-tailed test. Now, how do I know it's a two-tailed test? Because mu is not equal to 10, all right? The alternative hypothesis is saying mu is not equal to 10. It's either less than 10 or greater than 10. That's what not equal means. So if your sample statistics in this region, say suppose 5 is in this region, we also are going to reject the null hypothesis and state the alternative hypothesis that mu is not equal to 10 to be true. Suppose somebody else says, oh, I'm getting a sample statistic of 11, positive 11. And suppose 11's in this white area here, this non-shaded area. Well, this is the non-rejection region. So if the 11 is in this region, we do not reject the null hypothesis. We state that there's not enough evidence to reject the null hypothesis. Or another way of saying it is, 11 is not as far away as 15, and it's in this region here. So we say that, hey, you know what? This is just normal variation around the true population mean. It seems pretty normal that you can get an 11 for a samples mean when the population mean is 10. It's in this region here. Or maybe somebody else gets a 9 or an 8 for a sample mean, and it's in this region, this white region here. So this entire region between these two vertical lines is the non-rejection region. You get a sample statistic that's inside this interval here. We're going to not reject the null hypothesis. There is not enough evidence to conclude that the sample statistic, the sample mean, is sufficiently far away from the population mean, right? And if it's not sufficiently far away, we do not reject the null hypothesis. Again, this will become clear later. But the wording of the problem that we're looking at, whatever the problem is, will determine the alternative hypothesis. The alternative hypothesis is going to determine which of these three tests we're going to use. So if there's a not equal sign as the alternative hypothesis, we're going to use this two-tailed test. Now suppose the wording of the problem we're looking at, and we're going to use a proportion in this case here. Suppose the wording of the problem indicates that the alternative hypothesis, the competing hypothesis, is that the population proportion is less than 0.45. The null hypothesis is that it's equal to 0.45, but the alternative is that it's less than. Suppose in this case our type 1 error, probability of a type 1 error, or our level of significance is 0.01 or 1%. Now, this is called a lower tail test or a left tail test. I like the term left tail because it makes it clear which direction you're looking at. And since it's a one-tail test as opposed to a two-tail test, we're going to actually color in here an area that's equal to 0.01. Right? This whole area here is 0.01 or 1%. So we only have one rejection region when we have a left or lower tail test. And we put the entire amount of the level of significance, we put the entire amount there. Now, if we get a sample and our sample proportion is much less than 0.45, let's say 0.35, and let's say 0.35 happens to be in this region here, this 1% rejection region, we're going to reject the null hypothesis and state that the alternative hypothesis that p is less than 0.45, the true population mean is less than 0.45, is probably true. However, if we get a sample proportion that is less than 0.45, but not significantly far away, for example, 0.40, let's say 0.40 is in this non-rejection region, this white region, then we would say there's not enough evidence to conclude that the population proportion of 0.45 is not true. Okay, there's not enough evidence to reject it, and therefore we're not going to reject the null hypothesis. Remember, it does not mean that we accept the null hypothesis as true. We just don't reject it because it's still possible that it's false. All right, so this is called the 99% non-rejection region, 1% rejection region. Alpha determines the rejection region. Then finally, let's look at a third example. This is the example of what's called a right tail test or an upper tail test. Let's do this as an example with a population mean of 100 as the null hypothesis. And let's just say that the alternative hypothesis is that the true population mean is actually greater than 100. In this case, we're going to use a larger alpha, level of significance, as 0.10. So what do? Since it's a right tail test, an upper tail test, we're going to color in 10%, 0.1, as the region in the right tail here. That's our probability in here, 0.1. And then the rest of the curve to the left is the rest of the 90%. That's a non-rejection region. So once again, suppose we have a sample mean that is 120, for example, and suppose 120 falls into this rejection region here, we would say that there's enough evidence to reject the null hypothesis that u is equal to 100. Okay? And that's because 120 is significantly bigger than 100. All right, based on the statistics that we use. All right, we haven't learned how to do that yet. But suppose that mu is actually 105, or excuse me, suppose the sample mean is 105 that we get from a sample. Suppose 105 is in the white region here, the non-rejection region. Then we would say, well, 105 is not sufficiently different than 100 or bigger than 100 to come to the conclusion of rejecting 100. In other words, 105 seems reasonable that 100, we could get a sample of 105 as the sample mean when the population mean is 100, just due to normal variation, normal variability. So the three types of tests are determined by the wording of the problem. Wording of the problem determines the null and alternative hypotheses. Now the null hypothesis always has an equal sign, and the number that we put next to it will be given in the problem. Always know that this number in the null hypothesis and the number in the alternative hypothesis has to match. If the problem states that the alternative hypothesis is not equal to, as opposed to greater than or less than, then this is called a two-tailed test. And we take our alpha, the level of significance, and divide it by 2 and put half of that area to the left tail, half of the area to the right tail. And then we color in these areas and call them rejection regions. And then the area in the middle is the non-rejection region. And then we take a look at our sample statistic to see if it's in one of these rejection regions, which means we'll reject the null hypothesis, or if it's in this non-rejection region, which means we will not reject the null hypothesis. If the reading of the problem says that we have a left tail test, that means there's a less than symbol in the alternative hypothesis. Then we do a left tail test or a lower tail test. We take our entire alpha that's stated in the problem and we put that whole entire area in the left tail. We make that the rejection region. It's only one rejection region. And we make the rest of the area underneath the bell-shaped curve to be non-rejection. So if the sample proportion in this case is significantly less than 0.45 to the point where it's in this region here, rejection region, we're going to reject the null hypothesis, saying that the true population proportion there's enough evidence to say that it's less than 0.45 and not 0.45. Because it's highly unlikely that you would get that sample statistic if 0.45 is actually true. And we have the right tail test. So the wording of the problem says that the alternative hypothesis is greater than, as opposed to less than, or not equal to. It's greater than. So we know because it's a greater than problem that we're going to use a right tail test. We take our level of significance and we put that entire area into the right tail. We make that the rejection region, and everything to the left of that will be the non-rejection region. Once again, if our sample mean is significantly bigger than 100 to the point where it's in this region, this rejection region, we're going to reject the null hypothesis, and we're going to go with the alternative hypothesis. If it's in this white region, where it's not as far away from 100, we're going to say there's not enough evidence to reject the null hypothesis because the sample mean is close enough to the population mean where it could be just normal variability. Well, that was a lot of words. I hope you understand somewhat what I've talked about, maybe 10, 20%, hopefully, of what I talked about. When we do examples, which we will be doing over the next couple meetings, basically for the students at Rowan, this is going to be the last topic that we'll be doing, the hypothesis tests. So this will be for the remaining of the semester. We're going to be doing it using StatKey. So we're going to show you through examples, actually word problems, and we're going to use StatKey as a way of coming up with our decision whether to reject the null hypothesis or not. Okay. Those of you who are in my class at Camden County College, you'll see how to do it with formulas. Okay, so that'll be the technology that you'll be using. But regardless, it'll be starting next week. So please, hopefully you've seen this, and you can see this many times, this particular review. So I'm going to stop sharing now. And so that's it for today. I hope this was useful as an introduction. A little bit probably tomorrow, I will, for the students at Rowan, I will list the, I'll probably post in the
Okay, so let me get my video back on. All right, so that was the video I recorded last semester. And the reason I recorded it is because we're running out of time last semester for both of those courses. So people actually watch that on their own. Now, don't worry about what you heard because I'm going to be going over it with you. And I'm going to take a little bit of a different angle with you using StatKey to do a hypothesis test. One thing I want to do now is I want to share with you, see if it's available here. I'll share with you a PDF document. All right. Hopefully you can see this okay. Yell out if you can't see it, but I believe you can see this. And let me go to the, there's two PDFs here that are, I want to go through with you. Let me just review again what a hypothesis test is, and the way you write it and all of that. So a hypothesis test is where we have two hypotheses. One of them is called the null hypothesis. It is the hypothesis that is accepted in society. It's something that everybody agrees is true. And then somebody comes along and says, I don't think it's true. All right, so they come up with what's called an alternative hypothesis. So the null hypothesis is typically the hypothesis that it is accepted, currently accepted. It always has an equal sign to it. And the way we write it is, and it's very important that you know how to write this, you write it symbolically. You write it as H with a little 0 next to it as a subscript with a colon. And there are two types of hypotheses that we're going to look at, either a mean or a proportion. And hypotheses are always about populations, never about samples. So we're going to use the population parameter for the mean, if it is about means, mu, that's the Greek letter mu, or we're going to use the population proportion symbol, which is P. So this is just two examples of a null hypothesis. One example would be that the mean, the population mean, is 5. So it's accepted that for whatever we're measuring, the mean is 5. Or in this case, proportion is 0.35. Maybe 35% of the people say yes to a certain question on a survey, something like that. All right, so that's a proposed null hypothesis is something that's considered to be acceptable now. The alternative is somebody's come along, a researcher, and says, I don't think it's true. I don't think the mean is 5, or I don't think the population proportion is 0.35. I think it's something else. An alternative hypothesis has 3 possible symbols, either greater than, less than, or not equal to. The symbol that you use depends on the problem. For example, if let's say we're looking at a proportion, population proportion of 0.35, and you come along and say, I don't think it's 0.35. It could be greater than 0.35. It could be less than 0.35. I'm not sure, but it's definitely not 0.35. Then you will use as your alternative hypothesis that P is not equal to 0.35. You don't have an opinion of whether it's bigger or smaller, so we just say not equal to. All right, that's your alternative hypothesis. It's not equal to 0.35. It could be bigger, it could be smaller. On the other hand, you might think that the true population proportion is bigger than 0.35. So we're going to use this one right here, where it says P is greater than 0.35 as our alternative hypothesis. And it makes sense, right? If you think as a researcher, you think the population proportion is less than 0.35, you're going to use the one in the middle. So every problem, whatever the problem is, it'll be clear to you which of these three you would choose for the alternative hypothesis. But you would write the alternative hypothesis in one of these three ways, if it's a proportion, or if it's one of these three ways, if it's a mean. It can only be one of these three possibilities. Now, the number next to the null hypothesis, whatever the number is, has to match the null hypothesis number and the alternative hypothesis number have to be the same. They can't be different numbers, all right? It doesn't make any sense to have a null hypothesis with one number and an alternative with another number. It makes no sense to do that. So those numbers have to match. So a valid hypothesis test will have two hypotheses. One of them will have H0, and it'll have something that looks like one of these two up here, and then it'll have HA, the alternative hypothesis, and it'll be one of these six that are listed here. All right. Now the numbers, again, these are just random numbers I picked, okay? I know some students, they see numbers and they get fixed on it and they think that's the number that always will be there. You can't, obviously not, all right? These are just examples. So please look at these examples. The numbers are meaningless. They're just there as an example to show what a null and alternative hypothesis should look like when you write one. That's it. Now, the null hypothesis at the beginning is always assumed to be true. All right. And our job is to determine if there's enough evidence from our sample to conclude that it's not. That's really what we're trying to do. All right. Now, the sample data, it's going to, you know, if the null hypothesis is and the alternative hypothesis is all about a mean, then we're going to calculate a sample mean. All right, because that's an estimate of the population mean. That's what we're going to calculate. If the problem is all about a proportion, then we're going to calculate the sample proportion from the sample. I hope that makes sense also. Once we have that data, then what we're going to do is we're going to see if that sample mean or sample proportion is so far away from the proposed null mean or proportion, right? Whatever that number might be, okay? It's so far away that there's a very little chance that that sample statistic, sample mean or sample proportion, is just normal variation that we would expect if the true population proportion was mean of 5 or a proportion of 0.35, right? In other words, is it possible that the sample that we got, and the sample mean or proportion that we calculate is just normal sampling variability around that population parameter? Or is it just highly unlikely that's the case? And if it is highly unlikely, that's why we reject the null hypothesis. We just say, there's such a small chance that this sample mean or sample proportion would occur if the true population mean or proportion is such and such. It's so unlikely that we're just going to reject the null hypothesis, that number, that value, and we're going to say it's either going to be not equal to that value or less than or greater than, depending on the alternative hypothesis. That's what we're doing. We can't prove, 100% prove, that the null hypothesis is false. We can't do it because we don't know. You can't sample everybody. All right, we don't know what the true population mean or proportion is. All right, if we did, why bother with any of this? This is a waste of time. But since we don't know, and we have a hypothesis about it, let's test it and use probability. Use probability to determine if it's highly unlikely that the null hypothesis is true. It's just the same thing in a jury trial, criminal trial. You assume up front that the person who was accused of the crime, we assume that they're innocent, right? You've probably seen television shows like this. They're innocent until proven guilty. Well, what's proven guilty mean? It means there's enough evidence to go beyond a reasonable doubt. That's what they say in legal terms, go beyond a reasonable doubt, so that we have enough evidence to say, all right, I think this person committed the crime, and I'm going to reject the null hypothesis that they're innocent, and I'm going to say that they're guilty. Now, did you prove 100% that they committed the crime? No. All right, you never do that. It's never that foolproof. It's not 100%, but there's enough evidence to show that the person didn't commit the crime now, or did commit the crime. However, you could have made an error, right? That's the type 1 error. The type 1 error is that that the person committed the crime when they really didn't. All right, you've heard stories like that. People have been in prison for 30 years, and then there's DNA evidence to show that they didn't commit the crime, and they're released. But that's a mistake, right? That's a type 1 error. On the other hand, you've heard of cases where a person is not found to commit the crime according to the evidence, but they actually did commit the crime. Right? That's the type 2 error, where we don't reject the null hypothesis when the null hypothesis is really false. So errors are made, but we try to minimize those errors when we do research. That's the whole idea. All right. And that's what this chart is all about here. Right. The type 1 error, once again, is we reject the null hypothesis through the test that we do in the sample, when in actuality, the null hypothesis is true. So we've made that type 1 error. Now, if we reject the null hypothesis and the null hypothesis is actually false, we've made a correct decision, right? If we convict somebody of a crime and they actually committed the crime, well, good. That person should go to prison. All right. So that's a correct decision right there. That, by the way, the probability of rejecting the null hypothesis when the null hypothesis is actually false, that correct decision, the probability of that is called the power of the test. Okay. And we want that to be high. We want that to be high. We want a high probability that we've correctly rejected the null hypothesis. On the other hand, if the results of the test are that there's not enough evidence to reject the null hypothesis, when the null hypothesis is actually true, well, that's a correct decision too. But if we do not reject the null hypothesis and the null hypothesis is actually false, that's the type 2 error. It's called a beta. The probability of a type 2 error is called beta. Now, we're not going to go into beta very much. You just have to know the definition of it. Power of the test, you should know the definition of that also. But what's the most important probability here? The probability of a type 1 error. Why is that the case? It's because the purpose of doing research, the researcher has the alternative hypothesis. They hope that the null hypothesis is rejected because that's what they want. But it's possible when that happens that they've made a type 1 error. So they want to make sure that type 1 error is as small as possible. All right. And that's why they pick that up front, typically. This alpha, the probability of a type 1 error, is also called the level of significance. Typically, this is the researcher picks this up front. It could be 5%, it could be 10%, it could be 3%, whatever. It's a small percentage. Probability of a type 1 error. And that's what they do. Now, if it, as a result of the test, this is very important because it could be asked in the final exam, so you may want to write this down. If you go through a hypothesis test and you've concluded that you're going to reject the null hypothesis, the only type of error that you could have made is the type 1 error, because if you reject the null hypothesis, the only error that you could have made is that the null hypothesis is true, right? This error, type 1 error. If that's your conclusion in the hypothesis test, the type 1 error is the only error that you could have made. On the other hand, if through a hypothesis test you conclude that you're not rejecting the null hypothesis, not enough evidence, then the only type of error you could have made was the type 2 error. You see that? So if your conclusion is not to reject the null hypothesis, the only error that you can make, you just go across, there's a type 2 error. If you reject the null hypothesis, then the only type of error you could have made is the type 1 error. Look out for that in the final exam. That's a question that's typically asked, all right? So that's very, I mean, it's just logical. Hopefully you see it that way. But anyway, this alpha is called the level of significance. And we pick that before we actually do the research. That's what typically people do. It's an acceptable level of type 1 error. In case you do reject the null hypothesis, have a low type 1 error is a good thing, because that way you're confident that whatever result that you get is probably true. And I say probably because there's no way to know for sure whether the null hypothesis is actually false if you reject it. Once again, in that video, they talked about 3 types of hypothesis tests. There's the two-tailed test. And by the way, these 3 tests, the two-tailed test, the left-tailed test, and the right-tailed test, are all determined by the alternative hypothesis. If the alternative hypothesis has not equal to in it, it's a two-tailed test. If the alternative hypothesis has a less than symbol, it is a left-tailed test. And if the alternative hypothesis has a greater than symbol, it is a right-tailed test. All right? So we're going to actually go into StatKey and show you how to do a hypothesis test. But I want to now go to this other PDF here. And it's a 6-step process that you go through when you do a hypothesis. So 6 steps. It's important to know these steps, but again, you don't have to memorize them, because you'll have this next to you when you take your test and your final exam. This is one of the things that you're going to print out. All right. Step number 1 is to state the null and alternative hypotheses symbolically, right? Just like I showed you before. Once again, you use if it's a mean, you're going to use the Greek letters mu. And if it's a proportion, you're going to use the letter P. You have to make it look exactly like these. All right, the numbers have to match. If the null hypothesis shows 100 here, the alternative has to show 100, regardless of whether it's left tail, right tail, or two tail. And you must use these symbols. If it's a mean, mu, P, for proportion. Now, I've seen students who type in their answers in the core part of the final exam, where you have to write your answers out in Canvas. And I've seen them leave out the symbol. I don't understand why. Maybe they're not sure what the symbol is, but if you leave out any part of these things, you get 0 for that part of the test. It's not complete, and you get 0. You don't get partial credit. If you just put null hypothesis equals 0, you don't put the mu next to it, you get no credit for that. It has to be.
I'm sorry, I have a question. So to write mu,
yeah.
like, do you just like use the letter M, or is there like a specific thing?
Well, it's not an M. It looks like a U. There is I'm going to show you that when we do our review next week. I'll show you in Canvas how to write this. There's a choice there. When you type in your answers, there's some symbols there that you can choose. I'll show you where to find that. If for some reason you can't find it, then you would write MU. You understand what I'm saying? From U, MU. But you can't find it. But I'll show you how to type it in. The P, obviously, you can type in. The equal signs, less than or greater than, you can all type them in because they're all part of your keyboard. There is I believe in Canvas, there is a subscript and superscript choice. So you can write H with a little 0 next to it. That you can do. I'll show you how to do that. I believe you can write Greek symbols in there also. And I'll show you how to do that. Now, if you can't, you just type in the letters MU for mu. All right. Does that answer your question?
Yes, thank you.
Yeah, it'll be clear. Don't worry. I'm not going to let you hang out there and because during an exam, obviously you should know where all these things are, so you don't have to think about it. So that's step 1. All right, you have to get that right. Obviously, if you're doing a hypothesis test, you have to make sure that the hypotheses are correct, all right? Otherwise, you're going to be testing the wrong thing. Now, one of the things I have to mention to you that's very important, that for all hypothesis tests, it's not mentioned here, but you might want to write it down. The basic assumption is that you've collected a random sample. All right, it's a random sample that you've collected. Without being a random sample, you can't do a hypothesis test. You can't use probabilities. All right. So random sample, if you remember way back when, at the beginning of the semester, we talked about simple random samples, stratified random samples, cluster random samples, systematic random samples. Those are all examples of random samples. So it cannot be non-random. If it's non-random, you can't do a hypothesis test as it's being done here, that you would have to do something else, which is beyond the scope of this course. So that's a assumption. If that's ever asked in the final exam, that's the assumption that's made. All right, is that it's a random sample. All right, now I will go, when we do examples next time, I'll show you the types of things that you need to write down. But step number 2 is that you create what's called a randomization sampling distribution. I'll show you what that is in a minute in StatKey. All right, so you're going to create one of these, and on a test, I will give you one. All right, so it's not like you're going to create one, but you should know how it's created, what happens when you create one. But I'll show you one. All right, I'll show you what they look like, and then to answer questions about it, it'll be displayed, as part of the questions, just like when we did confidence intervals, the bootstrap confidence intervals, that we're going to do these types of these hypothesis tests using this so-called randomization sampling distribution. Then what you're going to do, and I'll show you how to do this, in the problem, you'll be given the sample statistic. All right, either sample mean or sample proportion, or you need to calculate it. It's possible that the sample, like for example, sample proportion, I might just give you the sample size and then the number of people who answered yes to a question. And then you simply take the ratio of those two numbers and you come up with your sample proportion. But regardless, the sample statistic will be an endpoint in this distribution. And again, I'll show you what I mean by that. Then it says and it gives you examples. It says for a left tail test, the proportion to the left of the sample statistic is what's called the p-value. I'm going to describe what p-value is in a minute. For right tail test, you'll have a area to the right. The proportion to the right of that sample statistic is called the p-value. And for a two-tail test, the proportion in the left tail plus the proportion in the right tail is the p-value. Again, this will make sense when we go through an example. Now, here's the big deal right here, step 5. Now, in the video and also in the handout, it talks about how to determine whether you reject the null hypothesis or not, and it creates these so-called rejection regions and things like that. Believe it or not, most researchers don't use that method. They don't talk about rejection regions, and it's really only in introductory courses like this one that they talk about that. However, they do talk about what are called p-values. And again, I'll tell you what that is in a minute. And I have found, I would say over 90% of all students prefer to make this decision, whether to reject the null hypothesis or not, based on p-values and not on the rejection region method. But I wanted to show you the rejection region method first, so that you could see the logic behind hypothesis testing. But the p-value method will be easier to do, and this is what most researchers do. They report a p-value. And then at the very end, there's the interpretation. The interpretation is basically you're going to say something like, at the blank significance level, what's the blank going to refer to? It's going to be that alpha, that level of significance. It may be expressed as a decimal or percentage, but you can write it like this, at the 5% or whatever the alpha is, you put that percentage in here. and you write it with these words, and then you do comma, you'd say something like, if you're going to reject the null hypothesis, you're going to say, there's enough evidence to reject. And what you do is you write the information about the problem. So if the problem is about um, height or weight or whatever it might be, you write those words in there, and you just write it in the context of the problem. There's enough evidence to reject. The hypothesis is that the weight is such and such, or whatever it might be. All right. So that's an interpretation, and you have to write it again using the words of the problem. You don't repeat step number 5. A lot of students do that. They'll say at the 5% significance level, I'm rejecting the null hypothesis. No, you've already said it in step 5. You actually have to say in the words of the problem what you're rejecting or not rejecting. All right. It has to be about the research. It has to be about the problem itself. So that is an interpretation part of it. All right. So those are the 6 steps that people go through. All right. So let's just stop sharing this. And let's actually go to StatKey. We only have about 10 minutes. So I'm just going to introduce you to that part of StatKey that does hypothesis tests. And then what we're going to do next time is do lots of examples. All right. Not all examples. And again, there's many of these examples are in that textbook that I was showing you about a week or so ago that the Locke family created, which they're the ones who created StatKey, and they have these examples in their textbook and also in StatKey. So I want to show you how to do hypothesis tests in StatKey. But I'll introduce it to you now. I do want to open up, actually, let me see something here. Oops.
And is it on Canvas, the stuff we went over?
All right, hold on 1 second here. I have to, give me a second here. All right. All right, so let me share my screen with you here. Let's see. All right, so what you're going to do in your browser, you type in the word StatKey, no spaces. And if you hit enter, it should, I mean, at least in my browser, StatKey comes up immediately. It's just www.lock5stat.com. All right, so choose that. All right, so again, you should be familiar with this by now because we work with this with confidence intervals. Remember, the Bootstrap confidence intervals were this middle column here. And don't worry about Bootstrap confidence intervals as opposed to hypothesis tests. I'm going to review all of that again on next Tuesday when we can do a review. All right, so now this last column here, randomization hypothesis tests, that's what we're going to be doing. And I'll start off with a test for a single proportion. I'll do that first, and then if I have time today, no, it looks like I won't have time today, but next time we'll do a single mean, and then we'll do difference in means, difference in proportions. All right, so we'll do all these next time. But again, I'm just going to open up a hypothesis test for single proportion. And this is the screen that you get here if you're running a randomization test for a proportion. Now, first thing I want to point out to you is the null hypothesis. They give you the null hypothesis right here. And if it's a proportion, it gives you the null hypothesis 0.5, but it doesn't have to be obviously 0.5. This is just defaulted to this. It's defaulting to 0.5. It doesn't mean that's what it should be. If the null hypothesis is some other proportion, you just change it in here. So if I click this box here, I can, let's say the null hypothesis is P is equal to 0.72. Just make up some number, 0.72. I'll type in 0.72. Okay. And there's my null hypothesis of 0.72. Okay? All right. Now, suppose, now, one thing that we can do here in this stack key is we can create our own data, our own sample proportion. All right. Now, how do we do that? Well, we have a sample size here. Suppose we have, let's say, 200 people in a sample being asked a question, and suppose that, let me think about this for a minute. Let's see. Suppose 145 of them say yes to that question, all right? So 145 divided by 200 is going to be our sample proportion. And it shows up right here, see it? 145 divided by 200 is 0.725. So that is my sample proportion. So my hypothesized proportion is 0.72, and my original, my sample proportion is 0.725. Everybody clear on that? All right. Now, these three boxes here determine the type of test that we're going to do. In other words, the alternative hypothesis. It's not going to be written down as P is not equal to. One of these three boxes will be checked. If the left box is checked, that means that P is less than 0.72 is the alternative hypothesis. If the right tail is checked, you cannot both, but if the right tail is checked, it means that P is greater than 0.72 is the alternative hypothesis. And if the middle box is checked, it means that P is not equal to 0.72 is the alternative hypothesis. Is that clear to everybody? So that those boxes there, if you see them checked, that tells you which of the three alternative hypotheses that we have, and it tells you the type of test, left tail, right tail, or two tail. That's it. All right. So I'm not going to tell you in a problem. If I show you one of these charts, I'm not going to tell you what the alternative hypothesis is, but we'll have one of these three boxes checked. So you'll just look up here. That's your null hypothesis in this box here. And the alternative hypothesis will be one of these three boxes. Not use the sample proportion in the hypothesis. This is just one sample. Somebody else could come up with another sample and have a different sample proportion. Get the idea? Because that's called sampling variability. From sample to sample, we will get different sample proportions here. So for this particular sample, this is the sample proportion. Now, to create what's called a randomization sampling distribution, we're going to use what we did before. We're going to create a bunch of these samples. Now, technically, you don't need to know the math behind how they do this. All right, it's a little complicated. Just know that what you're doing is you're creating what looks like many, many different samples of size 200. Remember, the sample size for each of the samples is 200 people in the survey. All right. So if I want to create 1,000 of them, there we go. And once again, if I just move my cursor around, it will show you that particular randomization sample. On the right there, it'll give you the information about that one that I'm pointing to. For example, out of 200, 148 answered yes to that question, which is a proportion of 0.74. 148 divided by 200 is 0.74. Okay? Now, this is the real key to this problem. Let's say we're going to be doing a right tail test. So let's just do this as an example here, a right tail test. Okay. Do a right tail test here. Notice that what defaults on this box here is 0.025. Right. What it's assuming here is that's your alpha, 0.025. But this is what I'm going to do. I'm going to take and be careful here. Don't use the randomization sample. Use the original sample proportion, 0.725. That's what the original sample proportion is. I'm going to click this box down here and type in the sample proportion of 0.725. Click OK. All right. There it is. Now notice all the red dots to the right of this. This is the number of red dots here will be 0.475 times 1,000. In other words, there's 475 red dots. That's the proportion of all the dots here. There's 1,000 samples. There's 475 of these samples that are R to the right of this sample statistic of 0.725. That number in here is what's called the p-value. The p-value is the probability or proportion, the probability that you will get, if the null hypothesis is true, of 0.72, that's the probability that you could get a sample of size 200 of that sample proportion or something more extreme than that, which means greater than that in this case here. And that is called the p-value. All right, we're going to talk more about that next time, but that's how you do it. And there's no calculations. In a regular statistics course, you have to use your calculator to come up with that answer. Here, that's it. And if I tell you that I've already entered the sample proportion into the graph, where do you find it? You find it down here because that's where I entered it. And what is this number up here? That's the p-value. That's the probability of getting this sample statistic or something even greater than that if we assume the true population proportion is 0.72. All right, so we're going to talk more about this next time. I'm going to show you many more of these types of graphs and how to interpret them. But you could see, I'm not asking you to do anything except for interpretation. All right, and knowing what all these numbers mean. I'm not asking you to calculate anything. I'm just displaying things to you. And it's your job to know how to read this graph. All right, that's your job. And it's so much easier than a regular statistics course. You should be saying thank you for making this as simple as possible, because it is simple as long as you know how to read this. All right, so we'll do this we'll continue with this next time. Any questions? All right.
When is the next quiz and when is the test?
Next quiz is next Tuesday, and the next test is a week from Thursday.
It's a week from Thursday.
And you have to make sure that you are available for both. There's no delays, there's no makeups, nothing.
Yeah. Okay, so next Tuesday is the quiz.
And the review for test 3. And
Okay.
then that Thursday, not this Thursday, next Thursday after that is the test number 3.
So next Thursday.
Next week is the big week, yeah, for all that. And then the Tuesday after that is your final exam. And that's it. Semester over.
Oh, we got another test. Oh,
No,
wow,
there's no other tests. No, that's it. We're done.
Wait a minute, I'm
Um,
confused. You
can you-
listed, excuse me. You listed 3 things. You said the quiz, a test, and a final?
Yeah, of course. It's on your syllabus.
Okay.
You should all know that by now, right? You should all know your syllabus tells you the schedule, and we're on schedule.
Yeah.
All right.
And what chapters are we doing for the test? I'm not doing well with these quizzes. That
All right. We'll talk about that privately. Let's talk about the private.
Can
There's other
you
people
stay
in here.
behind, Professor? Because I want to have a
Yeah,
conversation.
yeah. People who want to ask questions can stay behind. Everybody else can go, and we'll see you on Thursday.